dry either replaced by zinc. If sodium dry either replaced by zinc. If sodium dry either replaced by zinc. Sodium in dry either is replaced by zinc. Zinc only. Zinc. Then it is called Franklin reaction. Franklin reaction. Okay? Not in your NCERT textbook. Ready? Franklin reaction. Enough? The next method from your very same alkyl halide. Okay, next method. Method number D, I think. Fourth one from alkyl halide. Grignard reagent. Grignard reagent with active hydrogen species. Active hydrogen species. Grignard reagent with the active hydrogen species. Okay. And this is a reaction which is given in your textbook. A small version of this reaction is mentioned in your haloalkanes. Okay, I'll give you a detailed information about that. Listen, you know that is when an alkyl halide on treatment with the magnesium, which in presence of dry either solvent, what do you obtain? RMgX, and it is said to be Grignard reagent. Okay, so Grignard reagent is a good synthetic agent, good agent for the synthesis of alkane, or Grignard reagent is prepared from alkyl halide. So this method is simply considered from alkyl halide. Listen, if there is no dry ether here, if not present, what? If dry ether is not present in the reaction system, there may be chance for moisture. Okay, then the presence of moisture form alkane from Grignard reagent. So if there is no dry ether in the system, there may be the presence of moisture. The dry ether suppresses the presence of what? Moisture. If there is no dry ether, moisture may present, and the moisture may turns the Grignard reagent into RH alkane. RH alkane, and this is discussed in your haloalkanes. Okay, let me give you a detailed explanation about that reaction. Okay, this point is mentioned in your textbook, haloalkanes. Listen, if you have Grignard reagent, you know the polarization of Grignard reagent. Grignard reagent is R minus and Mgx plus, which on reaction with the active hydrogen species. Active hydrogen species, let it be AH. Okay, AH. The condition is that the species should supply H plus. Whatever be the A minus. Whatever be the A minus, the species should readily supply what? H plus. Then this bond may cleave. So an active hydrogen species in presence of Grignard reagent, what happens means the H plus goes to R minus, and it become RH. Or A minus with the Mgx, and it become Mgx. And this reaction known as Zerevitnov's method, but this is not given in your textbook. Okay, wait. H may be. What about A minus? A is OH here, right? What is H2O? H plus and so H2O means A is OH. This reaction is given in your textbook. What do you mean by moisture? H2O. So your Grignard with the moisture may forms what? Alkane. Okay, where moisture is a AH. So the first example is mentioned in your textbook. The rest is not in your textbook. Instead of moisture, it may be what? HCl. It may be. HCl can also supply what? H plus. So the A is changed, Cl minus. Okay. There is only change in what? A. Okay. Where A is in a byproduct. Your main product? Alkyl group of Grignard reagent with the hydrogen. That is the main product. Okay. Every H have same H, right? Where A is the change. And A is involved in the byproduct. Don't forget it, okay? So number 3, it may be NH3. It may be NH3. Then A will be NH2 minus. Okay? Or it may be any alcohol, ROH, CH3OH, CH3CH2OH like that, okay? What about A? OR, alkoxy group, right? Or something like that. Or maybe acid, RCOH. Or A group will be RCO. So any species, any species which can supply H plus is said to be active hydrogen species. Okay, where they all have different A group. For the reaction, R group is gained by H to become RH alkane, and A group with the MgX form AMgX. Okay. The first example that is given in your textbook. Okay. Generally, this reaction is known as Zervitnov's method or Zervitnov's reaction. Okay. But the name is not mentioned in your textbook. In your NCERT haloalkanes, this is given. Okay. And that is a case of this reaction. Generally, wait, first of all you have to copy this one. Okay, this is the actual idea, and you can show this one. Whatever, maybe that's up to you. Copy the order. Okay, and this point is given in your NCERT. So this is okay. If dry there is not present, what happened? Then the presence of moisture form alkane from like this. Okay, ready. Okay. explanations, reactions from NCERT is enough. Okay, but a small version of a small concept from each reactions are given in your textbook. Okay, but there are lot of possibilities or lot of examples in each case. Okay, you have to know everyone. There is no need of studying reactions other than from your textbook. But I'll give you some additional reaction after once after the whole chapter is over. Okay, ready? And this is not taken as an extra point. This where the small version of your content is mentioned in your textbook. Okay, so you have to know in a detailed pattern. Not only with H2O, but also with any species which can supply H plus, the reaction may be in the same pattern. Okay, there are some entirely reaction which are not mentioned in your textbook, like Coriolis synthesis. Okay, that all will be discussed once the chapter is. Okay, first of all, you should know everything about the reactions which given in your textbook with more and more examples. Okay, so it is over already. I'll give you some examples for practice here. Okay. This is CH2, okay. This is Grignard-Reagin and this is an active hydrogen species. Okay. First of all, you have to know what is A minus. You have to identify what is A minus. O, CH2, CH3 is A minus. Okay. So the main product is CH3, CH2, CH3, right? CH2H, CH3 propane, agreed. The alkyl is propyl, it become propane. What about the byproduct? CH3, CH2O, that is A minus, agreed. That is the A minus with the MgBr, fine. What about the next? Reaction with the magnesium become Grignard-Reagin, followed by hydrolysis become alkane. Okay, so it may forms Sig-butyl MgCl, then it become alkane. Ready? Here will be hydrogen. Alkyl halide with the magnesium forms Grignard-Reagin, followed by active hydrogen species H2O, alkane. The very same reaction. Okay, fine. And here the H plus is. What about the A minus? CH3NH. CH3NH. Agreed? So CH3, CH2H. That is the alkane. And the byproduct is CH3NHMg. Yeah. Okay. So the only change is in A minus. Okay. The rest are same. So you have to identify the A minus clearly. Then the reaction is very easy. NCERT asks. Which means the byproduct is important here. Okay, in all reactions the byproducts are not important, but in some reactions the byproduct is also important. Okay, so question something like in a sequence, the reaction may bring from the byproduct also. Okay, this is an example for that one. So here you have to know how to design the byproduct also in this case. Okay, questions from the byproduct may also ask. Okay. So that's all about the method of preparation from your alkyl halide. And this is a method of preparation from your Grignard-Reagent, where Grignard-Reagent is readily formed from alkyl halide. So these four are the method of preparation from alkyl halide. Okay. The next is number 1, 2, 3. Third one. The next is the second one have 4 subdivisions. Okay, and the third one, actually the method preparation number 3, strong reduction with the Hi in red phosphorus. Strong reduction with the Hi in red phosphorus. Okay, Hi means hydrogen iodide, which is in red phosphorus, and nearly for 50-degree heating also. Okay, the logic of this reaction is every monovalent function group replaced by 1 hydrogen, divalent function group replaced by 2 hydrogen. That's a logic. Okay, so monovalent Fg. Okay, you know the function groups all are elements which having more electronegativity than hydrogen, right? Like halogen, oxygen, right? Okay, so every electronegative atoms are replaced by hydrogen. So simply that is a reduction, removal of electronegative elements and addition of hydrogen. So monovalent function group replaced by 1 hydrogen, whereas bivalent functional group replaced by 2 hydrogen. Then only the valence is okay. Okay, listen. If I have an alkyl halide like this, RCH2X or RX, whatever it may be, RX or RCH2X. So this is a foreign atom, functional group, but it is a monovalent. So which one reaction with the hydrogen iodide in red phosphorus? What happens? This is a monovalent function group. Agreed. So it is replaced by 1 hydrogen. So what is the product? RCH3. Is it okay? Listen. If I have RCH2OH, that's a primary alcohol. Primary. So there is a foreign atom, OH. A function group, OH. That is a monovalent. So it is replaced by RCH2H or RCH. Or if it is a secondary alcohol like this, RCH OH R. Okay, so this is a foreign atom, but it is monovalent. OH is monovalent. Ready? So it becomes RCH2 R. Ready? This is aldehyde, right? Okay, so there is a foreign atom, but it is bivalent. Okay, ready? So it is replaced by RCH2H or it becomes RCH3. Okay, what is RCH3 actually? What are the products actually? The products are alkane. So simply the method of preparation of alkane. Okay, wait. If it is ketone, what happens? CH2 R. Agreed. You got the idea? Fine. If it is an acid, this is replaced by 2 hydrogen. Since it is divalent, this is a monovalent category. Replaced by it becomes Is it okay? And this is applied in your biomolecules. Okay. Wait, this reaction is actually given in your textbook. I'll give you an example. We know glucose. Biomolecules will be discussed later. Okay. What about the glucose? CHO, OH, H, OH, OH, CH2, OH, H, H, OH, H. And I think you're familiar with the structural evidences of glucose. Okay, there is a reaction. Your glucose on heating with the hydrogen iodide in red phosphorus. The forms normal hexane 1, 2, 3, 4, 5, 6. Normal hexane, which indicates that all carbon in glucose are linearly connected. There are 6 carbon, right? 1, 2, 3, 4, 5, 6. And the first carbon is a aldehyde. So O replaced by 2 hydrogen. It becomes CH3. Okay, which means that actually the reaction of HI in red phosphorus is given in your textbook, but it is actually in your biomolecules. This is a secondary alcohol. Already we have an hydrogen, and this OH is replaced by 1 hydrogen, become CH2, 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 CH2OH, CH3. Okay, so this reaction is applied here. Ready? So you have to know the reaction of HI red phosphorus. Okay. So the logic is this one. You simply replace the function group. If it is monovalent, you simply add 1 hydrogen. Bivalent, 2 hydrogen. Listen. If it is an ester, RCO, OR. This is OR is something like OH. Okay. If this hydrogen is replaced by alkyl group, then it becomes ester. That is the only change. Okay. So this OR is replaced by OR is a monovalent function group. This is replaced by 1 hydrogen, and this is replaced by you obtain the very same RCH3. Okay. Since the products are alkane, we can consider it as a preparation of alkane. So first of all, copy this one, the logic. Then you can show examples, and this is the example which is given in your textbook. Okay, the glucose conversion. Glucose. So in your textbook, this reaction is mentioned. So it is considered as, you know, the reduction of HI bar, HI in red phosphorus. Okay, so the reductions may be like this. Okay, so that you have to know, the reduction of HI in red phosphorus. So the logic is this much. Since the products are alkane, this is also considered as a preparation of alkane. The next method, that's a simple method. Hydrolysis of carbides. Hydrolysis of carbide. Okay. Carbide means carbon with a negative charge. The IDE suffix is usually for anions, right? Hydride, chloride, bromide, nitride, oxide, sulfide. IDE suffix is usually for anions. If the anionic species is carbon, then it is carbide. Carbide. Okay. Carbide means any carbon having N minus negative charge. Okay. But here we need carbide of methanide. Okay. Carbide of category methanides. Methanides means a carbide of C4 minus. Okay. Any carbon with negative charge is said to be generally said to be carbide. Here we need carbide of methanides. And if the methanides are hydrolyzed or cleaved using water, what happens means H plus from water attached to the to become methane. Okay, ready? This is the reaction. Okay, and we can choose the carbide of methanides like aluminium carbide Al4C3, and this reaction is given in your hydrogen chapter number hydrogen. Okay, and Be2C. Hydrolysis of Al4C3 is given water as an hydrolytic agent. What is the property of a water? You are studying the water in your hydrogen. Okay, so aluminium carbide is an example for methanide. So which one hydrolysis forms what? Methane. Beryllium carbide is also an example for methanide. Listen, what about the valence charge of this carbon? You know the valency of aluminum is 3, carbon is 4. So the carbon here is 4 minus. So this one hydrolysis forms no doubt methane. Methane is an alkane. Okay, but if you have calcium carbide, you know, it on hydrolysis forms. Here the ion is C2 minus. Okay, so here it forms ethine. So carbide of methanide only forms what? Methane. And aluminium carbide and beryllium carbides are examples for methane. What about the valency of beryllium? Beryllium is a second group element, +2. So 2 beryllium means +4. So carbon have to offer. So in these two, where carbon is in -4. So they on hydrolysis forms what? Methane. So the hydrolysis of aluminum carbide, methane, you obtain methane. Beryllium carbide of composition like this, you obtain methane. Okay. So simple method. Keep it in order. Your carbide should be methanide, okay? Then only you obtain methane. Otherwise, other products may form. So no need of studying the reaction with the stoichiometry. You have to simply know that hydrolysis of this aluminum carbide forms methane. Okay, no need of stoichiometry. What are the byproducts? Here will be AlOH thrice. AlOH. If H plus is consumed by carbon means the OH minus will goes to aluminum and it become AlOH thrice. Here BOH twice. That's the byproduct. Your main product is methane. Okay. So one set of preparation is there, that is said to be decarboxylation, but it is given in your textbook. Okay, decarboxylation of sodium salt. Put it as ID. Decarboxylation of sodium salt. Sodium salt of carboxylic. Wait. decarboxylation of salt of carboxylic acid. Decarboxylation of salt of carboxylic acid. Decarboxylation of salt of carboxylic acid. Ready? Decarboxylation of salt of carboxylic acid. Ready? Decarboxylation means removal of CO2 or COO. Okay? There are actually two types of decarboxylation which is given in your hydrocarbons. Okay? And you can bring the decarboxylation using soda lime. Soda lime is a mixture. Ready? For soda, that stands for NaOH. Soda, that indicates NaOH, and lime indicates CaO. Okay? Actually, the reacting component is NaOH. This should be in a 3:1 ratio. The reacting component is actually NaOH. CaO is a drying agent. Where NaOH is hygroscopic, moisture absorbing. NaOH readily absorbs what? Moisture. So CaO helps to keep the NaOH as dry. What is the purpose of CaO here? Which helps to keep the NaOH as dry. NaOH have a tendency to absorb. Tendency to absorb. Okay. To keep your NaOH as dry, we used what? CaO. So CaO is actually used to keep NaOH as dry. Okay, fine. That's the purpose. Wait, listen. Let me introduce the reaction. Okay. So this mixture is said to be soda, which is in the ratio of 3:1, where the reacting component is NaOH, CaO is a supporter. Fine. If we have a salt of carboxylic acid, like this, okay, with the N carbon, this molecule have N carbon. What are they? Carbon from this one with the carbon from R. Their total constitute N carbon. Don't forget it, okay? Carbon from R plus carbon from CON. Which on treatment is our soda lime. Soda lime means NaOH in CaO. Okay, so you can simply show the reaction like this. Okay, this become what? Na2. So the product will be RH. So your RCO may have N carbon, then RH may have one carbon is degraded. Well, that is a carboxylate group. So carboxylate group is degraded. That's why it is said to be decarboxylation. Simply the logic is this much. If you have a RCON, which on treatment with the soda lime, you simply replace this CONA by H. No need of writing the byproduct, okay? NO2CO3 is a byproduct. Listen, actually the mechanism, but it is not given in your textbook. You simply know the mechanism. Mechanism is anionic mechanism, carbanionic mechanism. What it is? Carbanionic mechanism. Listen, we have RCO minus here, okay, which on treatment with the base, what happened means this bond jumps to here. Okay, so the valency of this carbon become 5, right? Agreed. If this electron pair jumps to here, there will be a bond. You know the resonance structures, okay? If this electron pair jumps to here, there will become a bond. So the valency of this carbon become 5. So carbon leaves this electron. So carbon give the electron to R. So what happens? If this is jumps to here and this is clipped, this becomes CO2, right? This become, if this bond jumps to here, see double bond O. So this carbon could not accommodate this one. So it is shifted to alkyl group. So what about this one? This is CO2. So carboxylate CO2 is eliminated. Work forms R minus intermediate. R minus, that is said to be carbanionic intermediate. And this is a rate determining step. Rate determining slow step. You know the rate determining step, the meaning of rate determining step. So R minus plus CO2. So this is a rate determining step, which means the rate of this reaction depends on this step. Okay? Rate of this reaction depends on that step. When the rate of A to B increases, if a reaction is from A to B, when you can say the rate of this reaction is higher, if the formed B is more stable, right? If the formed B is more stable, then A have a ready tendency to become what? B. If the formed B is more stable, then A have a ready tendency to become B. Then the rate of reaction will be increased. So if this is the rate determining step, which means the slowest step, when it become fast? The very same concept. That depends on the stability of carbanion formed. Is it okay? So the rate of decarboxylation using soda lime depends on the stability of carbanion formed. Finally, once the carbanion formed, there may be a protonation from the system to form RH. This is the actual mechanism of reaction. We simply taking this one. Okay. So it is clear that rate of decarboxylation depends stability of carbanion. If the formed carbanion is more stable, then the carboxylate have a ready tendency to become the carbanion, which means rate determining slow step become fast. Okay, so maybe questions asked like this also. Arrange the following acid in the rate of decarboxylation towards acid, soda lime. Arrange these on the basis of rate of decarboxylation towards soda lime. So can you answer that? You simply make the carbanion. You simply remove the COH and bring the carbanion. Here it will be third butyl carbanion. Agreed? You know the stability of carbanion. Here it will be sig butyl. CH3, CH minus. Agreed? What about here? Normal butyl, primary. Okay? Which carbanion is more stable? In case of carbanion, the donating effect destabilizes. Okay, so which carbanion is more stable? Primary. You know the stability of carbanion. In case of carbon radical and carbocation, tertiary is more stable, whereas in the case of carbanion, primary more stable than secondary than tertiary. So the rate of decarboxylation will be like this. Okay, so to arrange this one, you have to know the mechanism is carbanionic. You have to know the intermediate formed is carbanion. Okay, the next is decarboxylation using electricity called electrolysis, where the mechanism is free radical, which is very well given in your textbook. So where the reactivity depends on the stability of formed free radical. Here it depends on the stability of formed carbanion. Both are entirely different. The stability of radical where tertiary is greater, whereas in the case of stability of carbanion, tertiary is a molecule with lesser stability. Okay, so concept may change. Ready? So no need of stick on with the detailing with the mechanism. You simply know the intermediate form is carbanion. Okay. 4 questions like this. Okay. So start from here. Decarboxylation of salt of carboxylic acid. First one using soda lime. Soda lime is a mixture of NaOH and CaO, which is in the ratio of 3:1, where NaOH have a tendency to absorb moisture, so CaO help to keep it as dry. Okay, and the reaction in a simple way. So N-carbon. What about the IUPAC name of this molecule? Sodium. Sodium alkanoate. RCOH is alkanoic acid. RCOH is what? Alkanoic acid. If hydrogen replaced by sodium, sodium alkanoate. Like ethanoic acid, sodium ethanoate, propanoic acid, sodium propanoate. Okay. Questions may be asked like this: decarboxylation of sodium propanoate using soda lime. So you have to write either. For that, you have to design the structure of sodium propanoate. You have to identify the structure of sodium propanoate. Then only you can show the reaction. Okay. So nomenclature is important. Basic nomenclature is important. So this molecule is named in the pattern of sodium alkanoate. Sodium alkanoate. For doing examples, this is required. You simply replace CONA by H. But for comparing this kind of questions, you have to know something about the mechanism. Okay. So this is the intermediate carbanion. Mechanism, carbanionic mechanism. Okay, so you show the mechanism and show that RDS. So the rate of decarboxylation that depends on stability of carbanion, and for that you can arrange a question like this. Okay. Listen, this is enough. Okay, RCOH plus NaOH plus CO is enough for making RH. No need of RCONA. Why? From RCOH itself, you obtain the product as RH. No need of showing RCONA. Why? There may be a chance for the reaction of RCOH with the NaOH. Carboxylic acid can readily react with NaOH, but alcohol could not react with NaOH. Phenol can. Okay. So if RCOH react with the NaOH, what happens? There forms a salt. Then the reaction may take place. Okay. So no need of showing the reagent or the reactant in the form of RCONA. It may be in the form of RCOH, because the system have an alkali to form RCONA. No problem. Okay. So RCOH or RCONA both are okay for this reaction. Ready? I'll give you some examples. In the case of example, you simply replace the CONA by H. That is the only idea. Okay. That's very easy. In this all reaction, the reagent is soda lime. Okay, so you simply show the product quickly. names of reactant? This is sodium. Ethanoic acid is the compound. Ethanoate or sodium acetate. What do you obtain? RH. R is CH3. So RH is CH4. No need of writing Na2CO3. The main product is enough. Okay. R is CH4. So question may be like that. So decarboxylation of sodium acetate. Choice. Ethane. Methane. Okay. So sodium acetate or sodium ethanoate. The reaction is okay. Okay. What about the next? You obtain ethane. Ready. Next, you obtain hydrogen. Hydrogen. What about this one? Sodium cyclohexane cyclopentane carboxylate. Here you obtain cyclopentane. Okay, no need of showing the hydrogen. Okay, bond line representation. So cyclopentane. What about sodium benzoate? Benzene. So this can be used as a method of preparation of benzene. Okay, will be written in your benzene. Next. So this is sodium isobutanoate. Sodium isobutanoate or isobutyrate. Here is the CONO, right? This is a CONO. Ready? CH3, CH, CH3, the rest is CONO. But CONO is replaced by hydrogen. So it becomes propane. Propane. Here will be an hydrogen, right? Okay. Agreed. So this become propane. Okay. So about decarboxylation using soda lime. One more decarboxylation is the last method of preparation of alkane called electrolysis. B or 2. One more preparation is the called electrolysis. Corpse electrolysis means you are given with a sodium or potassium salt. Sodium or potassium salt with the N carbon. Okay. Which undergoes electrolysis. Then you obtain RR type alkane in anode. I'll give you the detailed mechanism. The mechanism of this reaction is given in your textbook. The mechanism of Woods reaction not given. Okay. Mechanism of decarboxylation using soda lime is also not given in your textbook. In your textbook, the mechanism of cold electrolysis is mentioned. Okay. I'll explain. Simply the reaction is this much. For making product, this much. Okay, for writing the examples, this is a reaction. RCONA, one electrolysis become RR. Okay, what is a specialty means? N carbon molecule become, it's not 2N, 2N minus 2 carbon. Agreed? What about the carbon of, what do you mean by the N carbon? Carbon from R plus C. But 2 C's are decarboxylator. Okay, 2 carbon always lesser from the double. So you obtain 2N minus 2 carbon. 2N minus 2 or 2 of N minus 1 carbon. You know that from N carbon you obtain N minus carbon from, you obtain N minus carbon from N carbon using soda lime. Okay, but at the very same time, if it is electrolysis, you obtain double of n minus 1. Okay, that means, listen, if I have a molecule like this, CH3CON, okay, which on decarboxylation using soda lime, how much carbon are there? 2. What about the product? CH4, the carbon is 1, so this is n minus 1. Ready? Here, if it is electrolyzed, what about the product? The R is CH3. R become, so it become CH3. So here the carbon is 2. Okay, so what about the carbon in the top? Double will be then the bottom. Okay, which means if you have a salt of carboxylic acid which undergoes decarboxylation using soda lime, then how much carbon you obtain? The twice of it will be if it is in Kopp's electrolysis. Okay, that's the idea. And there are 3 types of Kopp's electrolysis also, because we require what? 2 carboxylate. So 3 types of Kopp's electrolysis also. What are they? Simple, cross, internal. Okay, listen. Wait. So first of all, symbol. This is used for symbol. Okay, these examples can be used for symbol. This is in a, symbol means between 2, say. Between 2, say. So sodium ethanoate. What about the product? If it is electrolysis, what about the product? CH3. The next, the product will be CH3, CH3. The product is hydrogen. Okay, hydrogen will be the product. This decarboxylated form hydrogen, or anode and cathode have hydrogen. This hydrogen is in anode. Wait. If the molecule is the previous one, sodium isobutanoate. Which one is the R group? This is R group. Agreed? Texting? No, the group is isopropyl. 2 isopropyls are combined to form 2,3-dimethyl butane. Okay. This all has to be what? Simple. Crossed means? Crossed means the very same. CH3, CONA plus CH3, CH2, CONA. What are the chances? CH3, CH2, CH3. Cross. Plus CH3. Just like your Woods reaction. Okay. CH3 plus CH3, CH2, CH2, CH3. So is there any chance for making methane? Is chance for methane using Kopp's electrolysis? Yes. CH3, CONA plus HCN is an existing compound. Okay, ready. HCN can undergo simple electrolysis, so it can participate in crossed one also. Ready. So what do you obtain? So methane can prepare using Kopp's electrolysis, but not by Woods reaction. One more chance is the, what it is? Internal. If I have a molecule like this, CH2COK, CH2COK, potassium salt is also okay. What about the product? You simply replace the COO and make a bond. That's the idea. So what do you obtain? CH2 double bond, CH2. Okay. So very same as your Woods reaction. where halogen is replaced and two R's are connected. Ready? Here CON is replaced and two R's are joined. That's only change. Okay. If two R are same, then it is simple, different, crossed, like that. Okay. So start from here. Complex electrolysis. The RR alkane in anode. Okay, I'll explain the mechanism after this one. This will be discussed later, okay? You can show the general reaction, and this is only for showing examples. Okay. Compare this one with the Woods reaction, okay? Then the ideas will be okay. Mechanism have a small change where the intermediate is very same free radical. In your Woods reaction, the intermediate is free radical. Like that, here also the intermediate is free radical. So there may be a chance for the rearrangement, which is mentioned in your Woods reaction. Conjugation rearrangement. Okay, so chances all are same. If CH2Cl, CH2Cl, sodium and dry, the product is CH2CH2. CH2Cl, CH2Cl, sodium dry, the product is CH2 double bond CH2. Internal Woods. Like that. CH2COK. COK or CONA, both are okay. CH2COK, CH2COK, sodium, potassium succinate is the molecule, okay. Potassium succinate. We obtain anything. Mechanism. After the mechanism, I will give the break. Okay. Mechanism, free radical. Free radical mechanism. Okay. This mechanism is important because questions from this mechanism may ask since it is given in your textbook. Okay. So you have to know everything. Ready? Examples are already over. Okay, simply know the mechanism because this is same as that of your Woods reaction. The intermediates are radical like that. Okay, so I'll explain the mechanism. This is electrolysis. You know the logic of electrolysis. there is an anode, cathode, and electrolyte. Okay, anode, cathode, and electrolyte. Listen, we know the electrolysis means the process of decomposition of an electrolyte by the passage of electricity, right? So when electricity passed, the salts decomposed into two, that is become 2RCOO minus plus 2Na plus, and the water as 2H plus plus 2H minus. Okay, so it's okay. This dissociated into like this, and okay, ready. So we have two anions here and two cations. According to electrochemistry principle, there is a competition. Okay, one may wins over the other. So here in anionic part, RCO minus become the winner, or here is the H plus. So losers are Na plus and OH minus. Okay, so they still exist in the, this anion goes to anode and this cation goes to cathode. For the losers, Na plus and OH minus, they are still in the tank. NaOH, which is in the electrolytic tank. Okay, since NaOH in the tank, the pH may increase. After this reaction, since NaOH is in the tank, the pH of the solution may be basic, increases. Fine. Now the reaction in cathode and anode. Okay, so in cathode, the species, which species goes to the cathode? H plus. So H plus from cathode, it absorbs 2 electron and reduced as what? H2. Okay, so in every Corpus reaction, cathode have hydrogen. Every Corpus reaction. But if the Corpus reaction is Corpus electrolysis with the sodium formate, anode also have hydrogen. Listen, the example with the HCONA, right? Hydrogen which is in anode. Every Corpus electrolysis, hydrogen as a product in cathode. Okay, but in the Corpus electrolysis of sodium formate or potassium formate, hydrogen which also formed in anode. In addition to cathode, also in anode. Don't forget it. That's why I especially written it as anode. Okay. Always hydrogen is in cathode. Fine. Now the reaction which is in anode. The ion which goes to the anode is RCOO minus. Listen here. Let's have a look about the 6 electron of oxygen. 1, 2, 3, 4, 5, 6, which means the valence electron of oxygen. In addition to that, if one more electron from the outside, then the molecule is said to be RCO minus, right? RCO minus means in addition to the 6 electron of oxygen, there is one more electron is from outside. Then only the species become RCO minus. Okay, so this is what anode. Anode, the process oxidation, which means removal of electron. So this carboxylate ion removes the extra electron. That means this electron. But if we have 2 carboxylate, it can release 2 electrons. So it simply oxidizes the 2 electrons to become RCOO dot. Agreed. This electron is loosed by carboxylate, so it becomes a odd electron species. So that is the intermediate. Carboxylate, free radical. Okay. Now the carboxylate free radical which formed in anode become become, since this oxygen is an odd electron, this oxygen asks electron for carbon. So this carbon cleave this bond to bring electrons. And it become CO2. Okay? That become CO2. How much CO2? 2 CO2. And here we have 2 R dot. They combine to form R dot. So this is the mechanism. Okay. So in your tank you have NaOH. In your cathode you have hydrogen. In your anode you have carbon dioxide evolution along with the alkane. Okay. So simply what is formed here is RCO minus become R radical. R free radical in Kolb's reaction. But in the case of soda lime reaction, RCO minus become R minus. Ready? So once this on electrolysis, it become R minus. But this on treatment with the NaOH become R minus. This become R radical. This become R. That you have to know. Okay, since you know the two mechanisms. This is important because given in your textbook. Question may be from this also asked. Okay. This is okay. This step is okay. RCOO minus means additional electron is there. Additional electron. That electron is lost. Since 2 RCO minus, it can lose 2 electron. So now its own electron is there and it become odd electron species. Since there is an odd electron species, the neighboring bond homolytically cleaved to become even. So that generates a free radical. Okay. Preparation is over. The next is chemical property. And the physical property of your alkane, alkyne. Physical property of alkane, alkyne are nearly similar or having a similar trend. So we'll be discussing in a separate section. Alkane, over. Okay. We combined in a very well pattern. Okay. The most important property is free radical substitution. Free radical substitution. In addition to radical substitution, there are some simple properties are there. So first we can discuss the simple properties like combustion, reaction with the steam, isomerization, pyrolysis. Okay. Then I'll explain the free radical substitution. Okay. So the first property, comparatively the chemical properties are less because alkenes are less reactive. Paraffins. Alkenes are known as paraffin. So, reactivity is comparatively low. Okay. Oxidation. Oxidation. Oxidation that oxidation means the reaction. Okay. Let the first oxidation and combustion. Okay. Physical oxidation and chemical oxidation are the ready. The first one is physical oxidation or combustion. Alkane two chance for combustion or in presence of limited oxygen have to be incomplete combustion. Okay, so in your physical oxidation or combustion, again two, that is complete, and you know the general idea, any alkane on complete combustion forms carbon dioxide and H2. Okay, so complete combustion means excess combustion in excess oxygen. Okay, not less. Ready? Okay, so maybe carbon dioxide combustion forms carbon dioxide and H2O. Now the difference in their stoichiometric equations. Okay, so I'll explain a general equation for balancing the combustion reaction of alkane. If you have an alkane with a molecular formula CN H2N plus 2, you have to show CN plus H2. CN H2N plus 2. This is a general formula of your alkene. So it so that it forms N CO2 and N plus 1 H2O. But this is only alkane. Only for. Okay, in addition to this, you have to study for any hydrocarbon where the carbon number is X, hydrogen number is Y. For any hydrocarbon with any hydrocarbon with oxygen forms excess oxygen form carbon dioxide and H2. And I think you are familiar with that. X plus Y by 4 O2 form X CO2 and Y by 2 H2. Ready? So the second one is most important because it can be applied in any. This is for any hydrocarbon, but the first one is for alkene only. Ready? Let I have an example. The combustion of butane C4H10 plus O2 CO2 plus H2O. This is an alkane, so we can use this one or this one. Ready? Anything. What about the first one? 3 into 4 plus 1 divided plus 1 divided by 2, which means 13 by 2. What about the second one? X, Y. X is, if it is in the second one, if it is in the first one, 3n plus 1 by 2 is 13 by 2. Okay. What about the second? 4 plus 10 by 4 plus 10 by 4 plus 5 by 2 will be 13 by 2. Both are same. Okay. So here NCO2. N is 4 CO2. Here it is X CO2. X is the very same 4. It's N plus 1 H2O. N is 4. So N plus 1 5. Here it is Y by 2 H2O. Y is 10. So both are okay, but this is only for alkane. This can be for any hydrocarbon. Hydrocarbon or alkane undergoes combustion. There are an amount of energy released called combustion enthalpy. Combustion, familiar in thermodynamics. It is the amount of energy released when 1 mole of a substance undergoes complete combustion with exhaust oxygen. So the energy released during this combustion is said to be combustion enthalpy. Okay, and combustion enthalpy, number of carbon in a molecule. You may arrange the molecules on the basis of combustion enthalpy. Okay, so the logic for the or the criteria for the comparison is, if number of carbon is increases, the combustion enthalpy will be higher. If the number of carbons are same, consider the branching decreases, combustion enthalpy will be increased. Okay, fine. Now, combustion. If for any alkane, this is a stoichiometry. Okay, where X and Y or N may change. Okay, they form only carbon dioxide and H2O. Stoichiometry may change, but you have to know the general idea or general equation. Ready? Show that. The first one, complete combustion.
ചാർജ് കുറവാണെന്ന് തോന്നുന്നു. അടുത്ത് ചോദിക്കുമ്പോൾ അത് ഞാൻ
ക്ലാരിറ്റി കുറവുണ്ടോ?
കുറച്ച് സൗണ്ട്
പറയണോ? ഓക്കെ ആണോ? കുറച്ച് combustion enthalpy is always negative because always energy released once a combustion takes place. Okay. Incomplete combustion. Which takes place in a limited supply of oxygen. Not stoichiometry for balancing that. Okay, where the carbon is known as carbon black. Carbon black. So this is a chance for limited combustion of, or this will be the combination of product in the limited combustion of alkane. Okay, if it is a excess combustion, complete combustion, CO2 plus H2O, and that is a stoichiometry. If it is in a limited supply of oxygen, then it is known as incomplete combustion. Then the possible combinations may either it may be CO plus H2O, or it may be the mixture of, if the oxygen is well limited, then C plus H2O. And the formed C is known as carbon black. Carbon black. Okay. That's all about the physical oxidation. Two chances, complete or incomplete. And the carbon black, write one point. Carbon black, also known as printer's ink. Printers, you know, printing. Carbon black, also known as printer's ink. Printer's ink. In bracket, used in printing industry. Used in printing industry and tires of automobiles and tires of, you know, the tires are made up by vulcanized rubber. Okay, for having a black color for the tire, they mixed with the carbon black. Okay, and it is also used as a ink in printing industry. That is the use of your carbon black. And tires of automobiles. Next, that is chemical oxidation. Okay. Chemical oxidation by means of any chemical reagents. It also poses the catalytic the first one, catalytic selective oxidation. If your alkane on oxidation forms primary alcohol, normally alkane of primary hydrogen oxides to form primary alcohol. Okay. Further oxidation forms aldehyde. Word oxidation means removal of hydrogen. Okay, CHO. Ready? Further oxidation forms acid, which means addition of oxygen. This is a normal oxidation sequence. Okay, alkane, alcohol, aldehyde, acid. Ready? So alkane aldehyde then become acid. Listen. Now depends on the we can skip the steps. For the oxidation of alkane to alcohol, we require copper in red hot copper. Copper in 5 Kelvin followed by treatment with 100 atm. It is mentioned in your text. Used CS2H, but you can skip this step if you are oxidizing and is molybdenum oxide. MO oxide. Okay, so if you have molybdenum oxide, then the oxidized product directly into okay. Or if you have manganese acetate, manganese CS3 COO twice Mn, the oxidized product will be acid. Okay, so the very same alkane which can be oxidized to primary alcohol or it can be oxidized to aldehyde, can be oxidized to acid. It depends on the selective nature of catalyst. Okay, so the reaction is under the control of catalyst. Listen, if I have ethane, ready, so you got CS3. If your ethane on treatment with the red hot copper, what happened? It become ethanol. Ready? If you done treatment with the molybdenum trioxide, it become ethanol. Okay, that is the idea. Manganese acetate. Then it will be. So you simply study the change. You have to know. Right. Okay. So this is the actual oxidation. Alkane to alcohol followed by aldehyde. Normally, if oxidations are proceeding, alkane become aldehyde then acid. Okay, but we can that nature of catalyst. Okay. Actually, the reagents are PCC and dichloramide for this one, and here bromine water like that. Okay, will be discussed in your alcohol and aldehyde. For the oxidation of alcohol to aldehyde, you can use PCC and dichloramide. This is a normal oxidation sequence. Okay, from alkene. But we can skip the steps. It is based on the heaviness of your catalyst. Okay, so questions may be like this. Okay, so depends on the catalyst, you use the product. First chemical, now the second chemical, number 2 with the dilute KMnO4. With the dilute KMnO4. With the dilute KMnO4. In bracket, Bayer's reagent. Dilute KMnO4. In bracket, simply it is Bayer's reagent. Okay. But there is a condition. Alkane with the tertiary hydrogen will only oxides. Okay, your alkane should have tertiary hydrogen. It will be oxides. Neither primary nor secondary. Listen. With the dilute. Why only the tertiary hydrogen? sp3 bond. sp3 bond. So CH bond, which is stands for sp to CH bond, sp-CH bond. Hydrogen which is in a triple bonded carbon, that is sp-CH bond. Hydrogen which is in a double bonded carbon, that is sp to CH bond. But here it is. So in carbon sp3CH bond, which means a hydrogen which is in a single bonded carbon. Okay, the chances are either primary, secondary or tertiary. 3 chances. Bond is primary CH bond is more stronger than secondary CH than tertiary CH. So tertiary CH bond is, hence it may be oxidized by direct KMnO4. Okay. So if I have N-butane, listen. If I have normal butane, what about the normal butane? Primary or secondary? Normal butane. Agreed. What do you mean by a primary carbon? A carbon branched only one carbon. This is primary. This is. So no. So if this N-butane on reaction with the direct KMnO4, there is no reaction. No reaction due to the absence of fine. But two butanes, N-butane and isobutane have tertiary carbon. A tertiary carbon may have one hydrogen, right? Because a carbon is branched to 1, 2, 3, so the remaining will be one hydrogen. So a tertiary carbon have one hydrogen. Ready? Some treatment for what happens? It may oxidize. Okay, alkane of tertiary hydrogen may oxidize. So this to become alcohol. Ready? So what is your product? Tert butyl. But the reactant is isobutane. Ready? If the oxidation is here, then it will be isobutyl alcohol. Since it is here, the product will be tert butyl alcohol. Okay? Isobutane become tert butyl alcohol. Fine. This is not tert butane, isobutane. hydrogen, alkene of tertiary hydrogen may oxidize because bond dilute KMnO4 can oxidize relatively weak bond, but the relative weak bond is a tertiary carbon hydrogen bond. We know that potassium permanganate strong oxidizing agent, okay? In D and F block elements, we already discussed it. A strong oxidizing agent, it can act as oxidizing agent in acidic medium, basic medium, neutral medium, like that, okay? So, if a substance is oxidized by KMnO4, what happens means the KMnO4 have a purple color. If a substance is oxidized by KMnO4, then the KMnO4 which acts as an oxidizing agent, right? If it acts as an oxidizing agent, it itself reduced, agreed. KMnO4 is reduced, so its purple color will be disappeared. Okay, so initially the KMnO4 have what? A purple color, but it's oxidized by KMnO4, where KMnO4 acts as what? Oxidizing agent. Then purple color will be decolorized. Okay, since the KMnO4 is reduced. Why it is decolorized? The KMnO4 itself becomes reduced since it is an agent. Alkene of tertiary hydrogen can decolorize KMnO4. Why? Alkene of tertiary hydrogen may be oxidized by. Okay, tertiary hydrogen will be oxidized KMnO4. So the color of KMnO4 will be. Okay. That's all about oxidation. Moving to the second chemical property. There is no chance for reduction of alkane because alkane is the most reduced form, okay? Alkane is the most reduced form. already seen it. Hi bar red phosphorus. Hydrogen iodide in red phosphorus is a strong reducing A which reduced everyone into alkane, which means alkane is the most reduced form. Okay, so there is no chance for reduction of your alkane. Chance for oxidation, we already discussed it. Okay, fine. So the second property, that is reaction with the steam. Reaction with the steam. Once your alkane with the steam, that forms a mixture of carbon monoxide and CO and H, and the mixture is said to be water gas. Water gas. Okay. So within on reaction with the steam. Steam means H2O in gaseous form. CO plus always the forms water gas. Okay. Representation for that. The only in the stoichiometry of CO and H2O. Moreover, stoichiometry CO and H2. Moreover, in the stoichiometry of H2. This is an alkane, right? Steam. CO. Okay, the general stoichiometry, if the number of carbon is n, then here will be NH2O. Here the number of carbon is 1. So here is 1 molecule of steam, 1 CO. So if the number of carbon is n molecule of steam, n molecule of CO, 2n plus 1 molecule of H2. Here the 2n plus 1 is 2 into 1 plus 1, 3. Okay. So the only change is change in stoichiometry. So this is the general equation. So it can be applied for any alkane. So your alkane on reaction with the steam forms always CO plus H2. Water gas. The mixture of carbon monoxide and hydrogen is said to be water gas. Ready. That's a simple reaction. Moving to the next. Pyrolysis or thermal cracking. Pyrolysis or thermal cracking. Lysis, the term breaking, cracking. Homolysis, heterolysis, you know. Pyro, the term heat. So your alkane is cracked into smaller alkane by means of heat. By means of heat, without oxygen. Without oxygen. If oxygen, it will be a combustion. Without oxygen, it will be a cracking. Okay, so write a point. Pyrolysis, thermal cracking. Write a point. Higher alkanes on heating with the, on heating in absence of, higher alkane on heating in the absence of air. Cracked to form lower hydrocarbon. Crack or splitted to form lower hydrocarbon. It may be alkane or alkene. Okay, so heating, crack it to form or split it to form lower air alkane on heating in the absence of air. They split it to form lower alkane. So let me show an example of carbon. Ready? degrees Celsius. 450 to 500 degrees Celsius is the temperature condition without oxygen. Okay, so you can heat your alkane in a 500 degrees Celsius so that the process thermal cracking or alkane will be better. Okay, there is no particular way for designing the product. Okay, there are number of chances. But if you have one, for example, if you given C2H6 as the first product, then you can predict the next one. Okay, what about the next one? Here we have 4 carbon and 10 hydrogen. Here it is ethane, right? 2 carbon and 6 hydrogen. Then the next combination will be C2H4. That you can predict. Okay, so along with the ethane, the product is ethane. So it's split into lower hydrocarbons. Ready? Consider another chance. If you have CH4, then the rest will be, if it is methane, the rest will be C3H6. Okay? There are a number of chances. You can't predict which one will be the product. Okay. If it is C4H8, then the combo will be hydrogen. Okay, so if one is given, then you can predict the next. That's the only idea in this reaction. Okay, we can't say that this will be the product. We can't predict that this will be the product. These all are the chances. Okay, so a particular product, chance for a particular product is not predictable here. Okay, there are chances. If one is given, you can predict the next. Ready? Used for cracking of higher alkanes in petroleum industry. Okay, in petroleum industry, petrol is actually a mixture of normal octane, isooctane, like that. So it is used to, or it is applied on the basis of cracking. So in petroleum industry, the thermal cracking is a widely used idea. Okay, but in our case, the question may be asked to a hydrocarbon is given and it is split into two or three, like that. Okay, you may ask to identify the reaction. So you can identify it as a thermal cracking or pyrolysis. Or if one is given, you may ask to find the other. That's the only idea for asking question from this one. Okay, or we can't predict this will be a particular one. Fine. So identification is the only which is used here or which can be asked here. A similar type of reaction is the isomerization. Okay, from the isomerization. AlCl3 anhydrous AlCl3 plus HCl. Okay. Ready? So okay, which one isomerizing agent? AlCl3. It isomerizes from another alkane. Okay, the only example in which we can predict the isomer is normal butane. The isomer will be isobutane. If the carbon is greater than 4, we have number of possibilities. Ready? But we can say that a linear hydrocarbon will be branched. This follows a mechanism where the rearrangement will be taking place. You are familiar with the rearrangement? Okay, rearrangement of alkene will be discussed in your alkene preparation of alkene. Okay, so So only one idea that we can predict that a linear hydrocarbon. Okay, so here also we can predict the product because this compound have only one isomer. Okay, if I have normal pendant from the car, chances will be increasing. Normal pendant become isopendane or neopendane. Isopendane or neopendane. Okay. Ready? So here also there is no logic for predicting a particular particular product. Okay, chances of predicting it. So this one, it is sure that in case of normal butane, it will be isobutane. Okay, from 4 carbon it is okay. More than 4 carbon, possibilities are increasing. If it is 6 carbon, we have 5 possibility. 7 carbon, we have nearly 9 possibility. Okay, chances, total isomers of alkane of 7 carbon is 9 and alkane of 8 carbon is 18. Alkane of 9 carbon is 35. Alkane of 10 carbon is 95. Okay, so we can't predict a particular one. Ready? But we may ask to identify an alkane is given which become its isomer. So the reagent may be asked. The reagent is anhydrous HCl3 plus HCl. Okay, and alkane of linear chain will be branched. Okay, it will become more branched. Ready? That you can write it down. Okay, alkane of linear chain will become a branched isomer. But which isomer, the prediction is not possible. Okay, it is only possible in 4 carbon. Okay, alkane of linear isomer may be branched. Okay. So the next, that is aromatization, where we can predict the products. Okay, aromatization. Here I have a logic. We predict a particular product. Aromatization or reformation. Reformation. So from the name itself, you are dealing with the chemical property of alkane. So you are given with the alkane. The alkane on with a particular reagent, it becomes aromatic. Aromatic means here only carbon. Aromatic derivatives. Alkane become benzene and derivatives. That is the aromatization. First of all, you have to know which one is the aromatizing agent. Aromatizing. In presence of what reagent the aromatization of alkane taking place. So the reagent is Cr2O3. Where is a promoter, supporter. L2O3 is a supporter. You know, promoter poison. Cr2O3 is the catalyst, where L2O3 is a promoter to increase the activity of Cr2O3. Either this combination or we do again the promoter, or your molybdenum oxide MO2 O3 plus L2O3. So simply aromatization in presence of heavy metal oxides. Transition metal, these are the transition metal, agreed. Chromium, vanadium, manganese. Okay, transition metal oxides are simply said to be heavy metal oxide. So aromatization in presence of heavy or Al2O3. Moreover, condition is there nearly 500 degrees Celsius and the pressure condition is up to 10 to 20 atm. So this is a reagent. Either it may be Cr2O3 plus Al2O3 with this condition, or okay, fine. This is a reagent. Ready? So show that. reaction have a logic, okay, and we can predict the products. Not like your isomerization or pyrolysis. We have a product here. Listen. The first actually what happened means the reaction is only taking place in the case of alkane of carbon or equal to 6. Your alkane should have at least 6 carbon or greater than 6 because your product is benzene and derivatives. Benzene minimum requires 6. So alkane of carbon 6 or above. Ready? First of all, treatment with the reagent. On treatment with the reagent, the cyclization. You open and cyclization and methyl cycloalkanes, alkyl cycloalkanes like that. Cyclized, the process dehydrogenation. Removal of hydrogen to form bonds from every carbon. Then it becomes an error for benzene. So finally, derivatives. Okay, wait. I have normal hexane. Normal hexane means CH3, CH2 times 4 times is enough. CH3. What is this one? Which one? Reaction with the reagents. 2, 3, 10 to DM. Okay, it become benzene. Total of 6 carbon. So it become, listen mechanism. This is pentane hexane. Let me show this one in this pattern. This is normal hexane. This also normal hexane. Agreed? 1, 2, 3, 4, 5, 6. In presence of catalyst, reagent, cyclization. Cyclization means the forms a bond here. Here forms a bond. CH3, right? This is CH3. This is removed and forms a bond. So what happens? Cyclohexane. This is the formed bond. Okay. So now it forms cyclohexane. Dehydrogenation. Dehydrogenation means we know that each corner have 2 hydrogen, right? Each corner have. So let me show the single hydrogens in each corner. Dehydrogenation. Hydrogen removed, that forms a bond. Here also removed, forms a. So what happens? It becomes. Okay. I'll give you 2 more examples, and this is the logic. Cyclization followed by dehydrogenation. അതെ 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 അതെ. ടോപ്പപ്പ് പറഞ്ഞാൽ വേണ്ട വേണ്ട. ഞാൻ ആവശ്യം കോൺടാക്ട് ചെയ്യാം. എനിക്ക് അവിടുത്തെ ബ്രാഞ്ച് മാനേജറിന്റെ കയ്യിലുണ്ട്. നിങ്ങൾ അവിടുത്തെ നമ്പർ കയ്യിലുണ്ട്. ഞാൻ ആവശ്യം ഉണ്ടെങ്കിൽ എല്ലാവരും കോൺടാക്ട് ചെയ്യേണ്ടത്. ആ പുതുക്കാറായിട്ട് ഞാൻ വിളിക്കും. Okay, so normal T, the next one normal. What is this one? CS3. What is this corner? CS2. 5 times CS3, just like CS3, CS2 5 times CS3. So total of 7 carbon. The molecule will be. Is it okay? So what will be the chance? It will be toluene. Okay. How it become toluene? Total we have 7 carbon, right? 7 carbon. So choose the first 6. First 6. CS3, CS2, 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 CS2. CS3, CS2, 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 CS2. First 6 carbons. And the rest is CS3. So this is the first 6 carbon, right? CS3, CH2, 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 CH2. So one more is there, right? The ring is made up of only 6 carbon because it have to form benzene. Agreed. So the X like this. Is it okay? So here it become methyl cyclohexane. Which one? Here is also one idea. Ready? Which one combination forms? Total. Okay. So one more you have to check. That is CS3, CH2, 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 and pardon. So there are 2 possibilities in normal hectane. Octane. Find the 2 possibilities. That's normal hectane. Yeah. Okay. So 2 possible products in the case of normal hectane. What are they? Find out. So maximum these 3 examples may ask. You have to think in this pattern. Okay, we have 2 chances. You can choose the listen, I'll give you a clue. You can choose the first 6 for cyclization, then the remaining will be an ethyl. So the either will be a branch. That's okay. Or you can choose the middle 6. Okay, and that become cyclized. So there will be 2-methyl, extra 2-methyl projection. Okay. So there are 2 chances actually. The first one using first 6, remaining is CH2, CH3. Cyclization to form what? That one cyclization followed by dehydrogenation forms. This compound is known as ethyl benzene. Ethyl benzene. The next chance, listen. The next chance. The ring made up of first, second to middle to 6 carbon. 6 carbons. So now first carbon, first CH3 will be here. Right? Choosing this one. So extra CH3 here to the next end. Agreed? Ready? So they connected by a bond. So it will be orthosilane. Orthosilane. Here is a CH3. Here is also a CH3. Orthosilane. Dimethyl benzenes are known as silane. Methyl benzene, toluene. Dimethyl benzene, silane. If it is in a relative ortho position, then orthosilane. Okay. So this is the idea for thinking. Okay, maximum of this may ask. Okay. Normal XA, normal FD, normal FD. Ready? So there is a specific logic for designing the product. You can predict the product. Okay. And the next, that is the most important reaction in alkene, free radical substitution. Okay, put it as a heading, free radical substitution. So one more chemical property is there, that is free radical substitution, which is considered as the most important chemical property of alkane. Free radical substitution. Free radical substitution. Free radical substitution. Actually, there are 3 types of radical substitution: halogenation, nitration, sulfonation. But in your textbook, halogenation is only given. So the most important is halogenation. So first we can discuss halogenation. Then we can write sulfonation and nitration. Okay. First preference or the most preference is for. And you are familiar with the halogenation for radical substitution. If I have methyl alkene, which on halogenated, normally the halogenation is chlorination or bromination. I'll explain why there is no chlorination or iodination. Okay, normally halogenation, chlorination or bromination. In presence of sunlight or heat. And you know the reaction, substitution reaction. So iodine is ready. So it becomes CH3, Cl+. I think you all are familiar with this. Okay. Now you have to know the mechanism, but the mechanism is explained in your textbook. Okay. Listen. Mechanism. Mechanism 3 steps. Listen carefully. Mechanism have 3 steps. The first one is chain initiation. Chain initiation. Free radical. Generation of radical substitution actually. Okay, that will be clear while explaining the mechanism. Chlorine on reaction with the sunlight. In presence of sunlight, the chlorine undergoes homolysis. Homolysis to form chlorine radicals. This chlorine radical be A. second step is the most important. Second step is chain propagation. Listen carefully. Now the free radical chlorine generated, right? So your alkane is methane, CH4, CH3H. This along with the free radical. Okay. So the alkane which is in presence of a chlorine, what happened means that homolysis. In presence of this chlorine radical, your alkane undergoes. And this is a rate determining step. So what happens? Free radical hydrogen is taken by chlorine to form HCl. Along with that, there will be a methyl free radical. Okay. So from the mechanism, it is clear that initially HCl is formed, not CH3Cl. Till CH3Cl is not formed, right? Initially it forms HCl. Okay. So carbon free radical or alkyl free radical form chain. Alkyl free radical. So it is clear that the rate determining step is alkyl free radical. So this reaction which is under the control of this step, which means the reaction that depends on the stability of free radical formed. This is a rate determining step. Okay, if the formed free radical is a most stable one, then the slowest step will become more fast. Okay, so the reaction is under the control of the stability of formed radical. Okay, so rate of free radical substitution that depends on the stability of formed radical. Okay, now the next step means in the propagation. If chlorine is limited, listen carefully, if chlorine is limited, you are given with only one chlorine. Only one chlorine. If chlorine is limited, you are given with only a Cl2. Or S is consumed here. Ready? Listen. If chlorine limited, one Cl is consumed, the Cl A is consumed, right? Where Cl B is there. Ready? That's B CH3 to form CH3C. So first forms HCl, then CH3Cl. If chlorine is limited, what happen means this will not be the step. It homolytically cleaves a next chlorine. If there is excess chlorine, what happen means this CH3 homolytically cleaves the next chlorine to proceed the reaction. So this is cleaved. So CH3Cl plus free radical. Then what happen means this free radical which absorb another hydrogen to become the very same step, become HCl plus to generate CH2 Cl free radical. If next chlorine is available, what happens? If next chlorine is available, what happens? The CH2 Cl free radical homolytically cleaves, and this is with this one CH2 Cl2 plus Cl. This is said to be propagation. Okay, it may propagate till all hydrogens are replaced by chlorine. If and only if chlorine is excess. If the chlorine is limited with the chlorine B, the reaction may proceed. Okay. And this is the step what we call the propagation. Okay, and the last one is chain termination. Termination means blocking or inhibiting the activity of free radical. The formed free radicals are combined to form a stable compound, or you can block free radicals. If free radicals are there may be a chance for homolysis. Okay, so chain termination may be blocking two free radical into Cl2, or blocking a methyl free radical with the chlorine free radical to CH3Cl, or blocking two methyl free radical. Blocking two methyl free radical. So ethane may be formed as a there is a chance for forming ethane as a byproduct, and this is said to be chain termination. So chain initiation, chain is very easy. In case of your chain propagation, that you have to look at. Okay, if what happens, the formed methyl free radical, which again homolytically cleaves the next chlorine and abstract one chlorine, so that forms a active radical. Okay, that active radical once again pick up the hydrogen to form the next radical. Then it proceeds. Ready? If and only if the chlorine is excess. Okay. So wait. Reaction. Then the major product will be CCl. Okay? Fine. Okay. You know the free radical stability. Which free radical is most stable? Tertiary. Before tertiary? You know benzylic free radical? You know benzyl? What do you mean by benzyl? A carbon which is alpha with respect to the benzene ring, right? Any carbon which is alpha means neighboring with respect to a phenyl ring is said to be benzyl. Okay, where benzyl free radical is the most stable free radical. Okay, then allyl. What do you mean by allyl? A free radical, a position which is just nearer, a single bonded position which is just nearer to a double bond, that is said to be allyl. Then you know tertiary, secondary, primary, like that. Okay, so it is clear that the rate of free radical substitution that depends on the stability of formed free radical, where the most stable free radical is benzyl. So the compound which can show ready electrophilic substitution will be a benzylic compound. Okay, so yes, this is over. Fine. So you have to understand the whole steps. Okay, that's important. Fine. Write a not point, not put it as a NOT, not. The point is clear from your mechanism. Rate of removal of hydrogen. Rate of removal of hydrogen. Rate of removal of hydrogen. Removal means it is clear that from the mechanism one hydrogen have to remove to form the free radical, and the removal of hydrogen which is in that rate that depends on the stability of free radical formed. The rate of removal of hydrogen depends the stability of free radical formed. Okay, rate of removal of hydrogen depends the stability of free radical formed. Okay, so which hydrogen removed easily means benzylic hydrogen. What do you mean by a benzylic hydrogen? This benzylic hydrogen, which is just alpha with respect to ring. Ready? Replace easily. Allylic hydrogen. Allylic means the hydrogen which is just alpha with respect to double bond. Okay, this is said to be the hydrogen which is just alpha with respect to double bond. That is said to be allylic hydrogen. Whatever it is. And this is the decreasing order of stability of what? Free radical. Okay, that will be the order of removal of hydrogen. Okay. Order of halogenation. Order of halogenation. Order of halogenation. The halogen is actually okay. Fluorination is the most one means fluorination or bromination requires sunlight, the presence of light, but fluorination so not fluorination is not since it's highly electronic reaction. Okay. The reactivity of fluorine is much higher, hence that reaction not preferred for making fluoroalkane. Okay, for making fluoroalkane. Taking place even in dark, moreover that is a vigorous reaction and that is not preferred for making fluoroalkane. Okay. The concept is your alkane which on treatment with the fluorine may forms what? Fluoroalkane, but this is not preferred. Then how you can form fluoroalkane means first you chlorinate your alkane. That's not a vigorous reaction, that's a simple reaction. Okay, followed by Schwartz reaction, halogen exchange method, Schwartz reaction in your haloalkane. Once you obtain chloroalkane, you can simply treat it with any fluorinating agents like AgF, Hg2F2, and the reaction is said to be Schwartz reaction. Then you obtain fluoroalkane. Directly the fluorination not preferred since it is exothermic. But if you want to prepare fluoroalkane, you can make the alkane into chloro followed by Schwartz reaction. Okay. This Schwartz reaction will be discussed as a method of preparation of haloalkane. Ready? What about ionization is very slow and reversible. So in order to proceed ionization, it need catalyst like HiO3. Okay. Ionization is very slow and it is reversible. For ionization, there should be a catalyst like HiO3 or agent catalyst. Okay, then only the reaction taking place. And what about the chlorination and bromination? Chlorination and bromination may taking place in presence of sunlight or high temperature. So it is clear that normally the halogenation means Simply, halogenation of alkane means either chlorination or bromination. Okay, iodination have some kind of difficulties, moreover chlorination also. Okay. And one more thing, which is more reactive, chlorine or bromine? Chlorine. So, comparing with the chlorine, bromination is slow. Comparing to the chlorine is slow and selective. Slow and bromination is much selective than chlorination. Like, what is the selective? The term selective. Okay, selectiveness means, listen, if I have a molecule isobutane, listen, isobutane, if chlorine radical formed, chlorine radical, and there is a chance for formation of chlorine radical and bromine radical. It is clear that chlorine radical may form easily comparing to bromine radical. So, what is this isobutane with a chlorinating agent or an agent which can produce chlorine? Chlorine radical easily generated and they okay, the chlorination is much reactive or much faster than what bromination. So once chlorine formed, they readily attack the hydrogens. Okay, but it is clear that mostly attack the tertiary, but there is a chance for attacking primary also. But chlorination is, because chlorination is fast, but slow and selective, which means bromination only taking place to the major or the most stable position. Most stable position. Bromination is very selective. This is formed in comparatively slow than chlorination. So once this bromine radical is formed, bromine radical carefully look into the molecule, then it attack the most stable position. So only tertiary formed in presence of, or in the case of bromination. Okay, the major product will be dominate, nearly 99%. But in case of chlorination, there is a chance for major and minor. Okay, why it is so means chlorination is much speed than bromination. So bromination is slow, moreover well selective. Bromine radical abstract the only. Ready? That is the meaning of slow and selective. We can do some examples. Okay? Listen, keep it in mind. So slow and selective means only major product dominate. In case of what? Bromination. Okay, listen. You have normal, which is, or which is. What's the difference? This molecule have primary and secondary position, right? What is this? Molecule is isocyanate. So there are two chances for alkyl group: C-butyl and N-butyl. It is already discussed. Okay, C-butyl chloride, and the second one is N-butyl. N-butyl is N-butyl, not C-butyl. Okay, which one will be the major? This is a replacement of, so this will be the major. But there is a chance for the formation of minor also in chlorination. In chlorination. Sigmated bromide. 99%. Okay, normally because bromination is much. Okay, not the minor product. isobutane? Iso. Maybe here or here. All are same. Okay. Ready? They all are same. Said to be isobutane. Questions may be like that. Okay, bromination of isobutane, the major chlorination of isobutane, the major product is third butyl chloride, isobutyl chloride. Okay, question may ask like that. So you have to know the. Okay, here the major only. Third butyl. Since it is bromination. What about here? Bromination, which means major. You have to show the major. Major means this will be the position where the most stable radical forms. Okay, most stable. What is this position? Allylic. What do you mean by allylic? A single bonded carbon near to a double bond. Okay, so this position is allylic, where allylic free radical generated and allylic bromination taking place. Okay. What about the second reagent? Bromine CCl4. It's not bromine sunlight, not bromine H nu. This is not bromine sunlight or bromine heat. It is bromine CCl. Bromine CCl4 were reaction taking place to the unsaturation. You know, normal addition of bromine to the bond will be discussed in the chemical property of alkene. Okay, now the product will be an addition product, not a substitution product. The mechanism may change. Okay, since this molecule have a double bond, there is a chance if bromine CCl4 is added, then there is a chance for electrophilic addition, asymmetric addition. Across the bond, two bromines are added. Okay, so you have to know the reagent. Okay, bromine sunlight, that's a substitution. Bromine CCl4 addition. If unsaturation is there. Okay, only if unsaturation is there. Not in saturated compound. What about the next one? Is this one. That's a benzylic portion, right? Benzylic position. Okay, the molecule is benzene product. A question like that is same. Bromination of ethyl benzene. Choices are first of all you have to know the name of this compound. 1-bromo. Even you know how to design the product, you have to know. Okay, 1-bromo, 1-phenyl ethane. Nomenclature is very much important. Even if you know how to design the product and you can select the most stable position, but you have to know how to name the molecule. Then only you can choose a choice. Okay, the choice are 1-bromo, 1-phenyl ethane, corresponding benzyl bromide, and one choice. So you have to know the correct name. Then only you can choose the choice. Then only you obtain the mark. Yo. These are the position. Allylic. Okay. A neighboring position to the unsaturation.